This document serves as an outline or a flow chart on how to solve thermodynamic problems. Okay, and this works for most problems that you're going to experience within thermodynamics. So basically, the first thing you want to do on any thermodynamics problem is what I call set the states. Okay, and what that really means is find the properties at each location or each state in the system. Now, the question you need to find out first is, what does set the states mean? Okay, so basically, am I looking for energy or enthalpy, U or H? Okay, so if it's a closed system like a piston in a cylinder, you're going to use energy U, or if it's a control volume like a heat exchanger or a turbine, you'll use enthalpy H anytime you have that fluid flow, that flow work that's occurring on that. So once you figure out whether it's a closed or open system, you're going to use energy or enthalpy, then you need to go figure out what your substance is. Okay, so that's step B here. Now, depending on what you have, if you've got water, okay, you're going to use your tables, right? So you have saturation tables, you have superheated tables. Okay, really any two properties will set the state here. Okay, the one caveat on here is if you have a liquid, right? Generally, at normal temperatures, we don't have a table. If it's at high pressures, we do have a table for water, table A5. Okay, and this is for liquid. Okay, if you don't have, if the pressures aren't high enough, what you do is you approximate that as a low pressure. Okay. Or I'm sorry, if it's at that low pressure, you approximate it as a saturated liquid at the temperature. So you use the saturation table, the temperature table, which I believe is table A2, and you go look up your value there. So that's how you set your states. You find your U, your H, whatever it is you're looking for each state within the system. If it's water, okay. If it's a refrigerant, such as R22, 134A, ammonia, or propane, you also use the tables. Okay. Now it's the same tables except there's no chance that we have a compressed liquid table. So again, for a liquid, you'll approximate it as a saturated liquid to look up your U or your H value shown there. Okay. If your substance is air, we have table A22 that you can look at energy and enthalpy, using the temperature. Okay. Now, if you need another state, okay, or you don't have temperature, okay, remember you have the ideal gas model that relates PV and R, PV and T, okay. Remember, R is actually R bar divided by the molecular weight, which for air is 28.97, okay. Now, the nice thing about air in the polytropic, and an ideal gas is the polytropic process, right? This is the last section in chapter 3, okay, where if you have constant pressure, N is 0, constant volume, N is infinity, constant temperature, N equals 1, and you can have this relationship to help find between pressure, temperature, volume, that sort of thing. So again, remember that section. It's a very helpful section, this idea of polytropic and what N is for different values. Okay. Now, the less common substances, such as carbon dioxide, carbon monoxide, oxygen, nitrogen. Okay, we have table A23, which gives you U and H values in molar terms. So again, when you look those up, remember to divide by the molecular weight of whatever substance you're using to get into the mass terms, the specific terms that we like to use. Again, these are going to be less common, but if it does come up, you're going to use that table. Okay. Again, remember, this is an ideal gas as well, so those polytropic processes work just as well for these. Now, helium, neon, and argon, okay, these are monatomic gases. We do not have tables, right? In general, if you have a table, use it. These are a case where you don't have tables. However, for these specific monatomic gases, specific heat actually is constant, so we can use specific heat equations to find delta U and delta H. So really all we're looking here when we set our states is looking for the temperatures, because then we can use the specific heats CP or CV, depending on if I'm looking for U or H, to find that change in enthalpy. Okay, again, only use these equations when you have helium, neon, or argon, these monatomic gases, because otherwise specific heat is not constant and shouldn't be used. Again, if you have a table, you should use it. Okay. Now, there are other weird, if it's some other substance, okay, you're going to have to use specific heat, as much as I don't like it. Okay. Again, the bottom line is, if you have a table, use it. Otherwise, specific heat is a good approximation, again, but the assumption that the specific heat is constant is not a very good assumption with temperature. So again, that's how we go through and set our states, right? You determine if it's U or H, you figure out what substance you have, whether it's water or refrigerant, air, what have you, and essentially you look up U and H values in your table. Okay, and if you don't have a table, that's when you finally move on to specific heats, the less optimal way. Now, this next we'll talk about, this is specific to second law things, so we'll talk about that after we introduce the second law. So this will not be part of the first law equation, so we'll skip all that. Now, the next thing is determine the mass. And again, maybe half of the problems you don't actually have to do it. They're saying, hey, give me the energy in kilojoules per kilogram, right, in terms of the mass. So you don't have to find it. Or it's just flat out given to you. It'll say, it's got a mass flow of 2 kilograms per second. So you don't have to determine that, okay? Now, there's several ways you can find the mass, right? If you know the volume, again, you can divide it by the specific volume to find the mass, okay? If it's an ideal gas, you can use the ideal gas model if you know PV and T, okay? If you know the volumetric flow rate, you can find the mass flow rate, okay? Conservation of mass, what comes in goes out, okay? Sometimes you know the heat of something or you know the work of something and you can use the first law to do it. You might know that the turbine's producing this much power. If you know H going in, H going out, you can calculate the mass flow using that. Okay, so again, this one you don't always do. It might be given to you, or it might, the answer might be in terms of mass, so you don't have to find it. But if you do, these are the different ways you can find it. Ideal gas, or volumetric flow, or first law equation, things like that. Okay, so now we set our states, basically found U and H. We know our mass or mass flow if necessary. Now the next step is to go find your work. Okay, so I've got a whole set for, if it's a closed system, a whole set for control volume. Okay, so some of the things, if it's constant volume, remember work is 0. Constant pressure, you get the really easy equation of P times delta V. If it's polytropic, we've got these equations. Again, these are all given in the last section of chapter 3, so you can go look up those. Okay, but you can find the work if you know it's polytropic or if you know it's constant pressure, depending on what you know. Okay, so we have those equations. Okay. The nice thing is if it's an ideal gas, then these polytropic equations are based on temperature, which you're more likely to have. You can find the work using that. Okay. Remember, isothermal is when n equals 1, right? So for polytropic isothermal, you use that equation. Okay. Or, you might know the heat, right? So if you know the heat, you've set all your states, you can easily find your work that way. So these are the different ways that you can find your work for a closed system. Now I have the same thing for a control volume, okay, which is, if you're finding the work, if it's an adiabatic, which oftentimes we do with a turbine and a pump, basically the work is just delta H times the mass flow rate, again, if the mass flow rate is important. We will get to this one later. This has to do with second law stuff, okay. Know that for a heat exchanger or nozzle, generally the work is 0, right? If there's no paddle spinning or anything like that, right? There's no work being done. So for a heat exchanger or nozzle, there's no work. The other way we could find work is, hey, if I know the heat transfer, right? I can use a heat transfer along with the H in, H out to find that work. Again, this would be similar to the adiabatic, where I know the heat transfer is 0. If I know the heat transfer is something else, I would use the first law equation. Okay, so now we set our states, we find our mass, we determine the work, whether it's for a control volume or a closed system, and then we're left with finding the heat. Okay, and to find the heat, we just use the first law equation, right? Because we know our states, U1 and U2, we now know our work, we can find our Q from that. Or the same idea with a control volume, right? We know our power, we know our H values, we know our mass, we can find the heat from that, okay? So again, that's the process that we use to go find this. And then if it needs to find efficiency or things like that, you'll use the equations depending on what we have. But at this point, we know all of our heats, we know all of our works, we should be able to find whatever we need to. Now, this last section is for, again, using the second law, so I'll introduce that a little bit later. But this flow chart is kind of helpful, kind of steps you through exactly how to solve it. And if you follow this by first setting your states, right, which is finding U or H, for different substances, water, refrigerants, air. Again, use the tables if you have them. If you don't have a table, then you can move on to things like specific heats. But again, the tables are the way to do it. Okay, so you use those tables to set the energy or enthalpy of each state. Then if needed, go ahead and find your mass. Once you have your mass, go and find your work using the values that you've got, U's and H's or P's and V's. Okay, but you've set all your states, so you should know all the properties at this point. So just picking the right equation for if it's a closed system, isothermal, or if it's a adiabatic control volume or whatever to find that. Once you get your work, then you just use the first law to find your heat.